Hello everyone. In this video, we are going to discuss singularities. Singularities are the points at which a complex function f of z is not analytic. Observe the following complex functions. F of z is equal to 1 by z power 9 sin z by z e power z minus 1 divided by z 1 by sin 1 by z log z and e power 1 by z. All the above functions are not analytic at the point 0. However, in the neighborhood of the point 0, there is a point at which the function is analytic. Before see the definition of singularity, I am going to define the analytic function. A complex valued function f of z is said to be analytic at the point z0 in the extended complex plane if the following two conditions are satisfied. F of z is differentiable at z0 and f of z is differentiable in some neighborhood of z0. Now, the definition of singular point. A point z0 is called a singularity or a singular point of f of z if f of z is not analytic at z0 and f of z is analytic at some neighbor points of z0. See the example. Consider the function f of z is equal to 1 by z, and from this f dash of z is equal to minus 1 by z square for all z not equal to 0. Therefore, f of z is not analytic at the point z equal to 0, but it is analytic in every neighborhood of 0. Therefore, we can say f of z is analytic except to the point z equal to 0. Hence, z equal to 0 is called the singular point of f of z. There are two types of singularities. One is isolated singularity, another one is non-isolated singularities. So the definition of the isolated singularity is as follows. A singular point is called an isolated singular point or an isolated singularity if the neighborhood of z0 contains no other singular points of f of z except z0. That means f of z is analytic at all points of neighborhood of z0 except z0. Now, the definition of a non-isolated singularity is nothing but a singular point z0 is said to be a non-isolated singular point or a non-isolated singularity if z0 is not an isolated singular point. Consider the function f of z is equal to z plus 1 divided by z square into z square plus 1. So, this is the example for isolated singular point. Let the denominator z square into z square plus 1 equal to 0. Solving the denominator z square into z square plus 1 equal to 0, we can have the next line z square equal to 0 or z square equal to minus 1. This implies z equal to 0 or z equal to I or z equal to minus I. There are three singular points such as 0, I and minus I. Consider the following example. This is the example for non-isolated singular point. Consider function f of z is equal to log z. Let z equal to r e power I theta, where r is varying from minus infinity to plus infinity and theta is varying from minus pi to plus pi. Then log z is equal to, then taking log on both sides, log z is equal to log of r e power I theta. So from the apply the operations on logarithm in the right hand side we can have log r plus log of e power I theta. From this we can have the next line log r plus I theta. If the value of r lying between minus infinity to 0, the log r does not exist. Therefore, all the points on the negative real axis left side, that means the left side of the y-axis are called are non-isolated singular points. So this is the definition for principal part. Let z0 be an isolated singularity f of z. Let delta greater than 0 be such that f of z be analytic in 0 less than modulus z minus z0 less than delta if f of z can be expressed as a Lorentz series expansion about the point z minus z0 by f of z is equal to summation n equal to 1 to infinity bn by z minus z0 power n plus summation n equal to 0 to infinity a n times of z minus z0 power n. Then we can have the two definitions called the integral part and the singular part. So integral part is nothing but summation n equal to 0 to infinity a n times of z minus z0 power n, and the principal part or singular part is z minus summation n equal to 1 to infinity bn by z minus z0 power n. Thank you.